In this section, we're going to look at what I call the GCDLC theorem, greatest common divisor linear combination theorem. So let's start with a definition of what we mean by a linear combination. You may have run into that word in vector spaces when you're talking about linear combinations of vectors. It's a similar concept here, only we're just dealing with integers. So a linear combination of two integers, a and b, is just an integer of the form a times x plus b times y, where x and y are, again, integers. You might also call it an integral linear combination, just to emphasize that x and y are integer values. So the GCDLC theorem says the following. It says that if you start with two integers, not both 0, and I let d be the greatest common divisor, then I can express d as a linear combination of a and b with integer coefficients. In particular, d is going to be the smallest positive linear combination of a and b. This theorem is also referred to as Bézou's lemma, and there's several proofs of it. I'll give you two different types of proofs. One is a constructive proof, and I'll just do that with an example just to show you how it works. And then we'll give a rigorous non-constructive proof first. Okay, we claim that every additive subgroup of the integers is a cyclic group generated by some element d. So a cyclic group, I'll just put parentheses, or you could write it like this. I've used the parentheses to denote the idea of a principal ideal generated by d, but it's just the set of all multiples of d. So d times x, where x is some integer. Okay, so how do we prove this? So I'm going to let H be a subgroup of the integers under addition. So we're thinking of addition as being our binary operation. Well, if H is 0, so the set just containing 0, then I'll just take d to be 0. And that's trivial. So let's assume h doesn't equal 0. So in this case, it's got to contain some non-zero element, and being a subgroup, if it contains some negative element, let's say, it would have to contain its additive inverse. So we can say that H contains some positive integer. Okay, so let's look at the set of all positive integers in H. Is in H. Well, this is a non-empty subset of the natural numbers. And therefore, by the well-ordering principle, S must contain a minimum element. So by well-ordering axiom, S has a minimum element. And we'll call it D. Okay, so our claim is that every element in our subgroup H is a multiple of D. So H is the set of multiples of D. Okay, so we need to show that H is both a subset of this cyclic group and that this cyclic group is a subset of H. And I claim one direction is trivial. So certainly the set of all multiples of D is contained in H. And why is that? Well, since D is an element of H, and H is closed under addition. Meaning that D plus D, D plus D plus D, so every multiple of D is going to be in H. And also, H is closed under subtraction, or contains additive inverses, so all the negative multiples of D. So we'll just say H is closed under addition and contains additive inverses. Okay, so that direction is easy. The more interesting part is why must every element in H be some multiple of D? Now let's show that H is contained in this group, cyclic group generated by D. Okay, so let H be an element of H. And I want to show it's a multiple of D. So if I want to show something's a multiple of D, let's divide it by D and show that there's no remainder. So by the division algorithm, maybe we'll go to the next page, H equals QD plus R for some Q and R in the integers with the remainder strictly smaller than D. Okay, now notice that R is H minus Q times D. Well, this is in H, and this is a multiple of D, so that's back in H, and H is closed under subtraction, so this is an element of H. Aha! But R is smaller than D, so thus, by the minimality of D, what do we conclude? We must have that R, the remainder, has to be 0. Otherwise, it would be a smaller positive element in the set H. And then R equaling 0 means that H is a multiple of D. So H is QD, which is an element of the cyclic group generated by D. QED. Okay, now let's go back to the GCDLC theorem. So I let A and B be integers, not both 0. And I'll let D be the greatest common divisor of A and B. Okay. So we claim that D is some linear combination of A and B. So let's state our goal again. D equals AX plus BY for some X and Y in Z. Well, what am I saying here? I'm saying that it's some multiple of A plus a multiple of B. So what subgroup should I think about? Let's let H be this subgroup. Take the set of all multiples of A plus the set of all multiples of B. So this is precisely the set of all objects of this form where X and Y are integers. And clearly, this is a subgroup. It's closed under addition, it's closed under subtraction, it contains the 0 element, so an H is clearly a subgroup of Z, and it also clearly contains non-zero elements. And so by the preceding lemma, it is a cyclic group generated by some element D. We know H equals, well, I've already called D the GCD, so let's call it E for some and positive integer. In the lemma, we said non-negative, but we know that H contains non-zero elements, so there'll be some positive integer E here. And I claim that E must equal D. So why is this? Well, okay, so A is in H. Since A is in H, we know that A has to be a multiple of E, so E has to be a divisor of A. And since B is in H, we know that E divides B. Thus, E is a common divisor of A and B. Okay, next, we want to show it's the greatest common divisor. So suppose you have some other number that is a common divisor of A and B. And we claim it's a divisor of E. So the point here is that since E is an element of H, it must in fact be some linear combination. And this is our definition of H right here. There exists X and Y such that E equals AX plus BY. And therefore, if you have any common divisor of A and B, it must be a divisor of E. So I've called D the GCD, so since D is a common divisor of A and B, we have D divides any linear combination, so D divides E. So we've got E is a common divisor of A and B, and the greatest common divisor is a divisor of E, thus E must be the greatest common divisor. And we've also shown that we've got the linear combination right here. QED. Okay, now I said there was another way we can get to the GCDLC theorem, and that's just through the Euclidean algorithm itself, using a method of back substitution. So this is how we actually solve the equation AX plus BY equals D, where D is the GCD. Now I'm going to show you actually two methods of solving this equation. The first method is just back substitution. So let's go through how we calculated the greatest common divisor of 126 and 49, and then express it as a linear combination of 49 and 126. So following the Euclidean algorithm, we had 126 is 2 times 49 plus 28, and so on. So we did this earlier. And now the second part is the back substitution. So that's the new step. So this is where I want to locate the GCD, which is right here at 7, and express it as a combination of 126 and 49. And so I start with equation 3, where I have 7 is 28 minus 21, and then I keep substituting in by working my way back. So by equation 2, 21 can be expressed in terms of 49 and 28. So I substitute in that 21 is 49 times 28. And that gives me a combination of 28 and 49. It gives me 2 times 28 minus 1 times 49. Then I go back to equation 1, and I say, aha, here 28 is 126 minus 2 times 49. Oops. That. So 28 is 126 minus 2 times 49. And then grouping these together, we get 2 times 126 minus 4 minus 5. So minus 5 times 49. And there you have it. 7 is the linear combination 2 times 126 minus 5 times 49. Now you notice in this technique, it's not a real efficient way of solving this equation here, because it required me to first lay out all of these equations and then kind of go through the equations a second time to come up with the final solution here. So the second method, I call the array method, allows you to do both tasks in one, you're just going through it one direction. You don't have to go back and forth through the system. So in the array method, what I do is I draw an array like this. In the top row, I'll put linear combinations of 126 and 49. Second row, I'll put x. And the third row, I'll put y. And then I just start forming various linear combinations. So I could put x to be 1 and y to be 0, and I get 126. Or I could let y to be 1 and x to be 0, and I get 49. And then I just perform the Euclidean algorithm on the top row. So perform Euclidean algorithm on the top row. And the other rows will just keep track of the x and y values. So I first want to subtract 2 times 49 from 126. So if I call this column 1 and this column 2, I'm going to take column 1 minus 2 times column 2, and that gives me 28. And then do the same thing with each of these entries. So 1 minus 2 times 0 gives us 1. And then 0 minus 2 times 1 gives me negative 2. And this column is telling me how do you express 28 as a linear combination. 28 is 1 times 126 minus 2 times 49. Okay, the next step would be column 2 minus column 3. So 49 minus 28 is 21. 0 minus 1. 1 minus a negative 2. That gives me 21 as a linear combination. And then column 3 minus column 4 gives me 7. So 1 minus a negative 1 is 2. Negative 2 minus 3 is negative 5. And bingo, I'm done. So the final step in the Euclidean algorithm is just to produce the 0 by subtracting 3 7s from 21, but I don't even need to bother writing it down, because as soon as you get 0 here, that's indicating that this is your greatest common divisor. And so we've shown that 7 is the GCD, and at the same time, we've established that 7 is 126 times 2 plus 49 times negative 5. So from a programming point of view, this is much more efficient, because I don't have to store all of that data that was in the original Euclidean algorithm array. All of this information up here, don't need to worry about. Okay, now this theorem can extend to more than two elements. If I want to find the GCD of k different integers, then in fact it's true that there exist integers x1 through xn such that the linear combination here is the GCD. And once again, the GCD is the smallest positive such linear combination. So for example, let's show how the array method would work for the GCD of 6, 15, and 20, and expressing it as a linear combination of these. So this time I'll have 6x plus 15y plus 10z. X, y, z. And you can set it up any way you like here. You don't have to start with 1, 0, 0. You just want to get some starting numbers here. So 1, 0, 0 would give us a 6. 0, 1, 0 would give me a 15. And 0, 0, 1 gives us a 10. And then just start reducing these numbers. So you're thinking to yourself, calculating this GCD, and I'm going to knock down the 15 and the 10 by subtracting the multiples of 6 from these numbers. So let's subtract 2 6s from 15 to give me down to 3. And let's just do it one step at a time. So I'm going to take the 2 times the first column from the second column. So 0 minus 2, 15 will be 1 minus 0, and this is still 0 here. And then I can very easily combine these two columns to get a 1. And there's all sorts of routes you can take here. And as soon as you get a 1, you're done. You know, the GCD is equal to 1. So I'm going to take the third column and subtract 3 times the fourth column. Third column minus 3 times this would be 6. 0 minus 3, 1 minus 0. And then, of course, we'd have 0 on the next step, so we stop. The GCD is 1, and we get that 1 is 6. That's the x value. 6 times 6 plus negative 3 times 15 plus 1 times 10. And that's the linear combination we're looking for. Let me double check. 36 plus 10 is 46 minus 45 is 1. Okay, so it checks out.